you students for the first session on transition metals. All of you know about the arrangement of elements in the periodic table. In the S block elements, lying in groups 1 and 2, the last electron enters the outermost S orbital, NS orbital. Similarly, in elements occurring in groups 13 to 18, the last electron enters the outermost p orbital or np orbital. In those elements which occur in groups 3 to 12, the outermost electron or the electron which enters last enters the n-1 d level or penultimate d level. You know, 3d level is filled only after 4s. That is why the first row of transition metals in which the 3d level is filled occurs in fourth period. Similarly, the transition metals which occur in the fifth period have that 4d level filled, and the elements in which the 5d level is filled, they occur in the sixth period. Mainly we take these three rows of transition elements for consideration. Now, how do we write the general electronic configuration of transition elements? You have studied it already. You know, the general electronic configuration of transition elements is NS 1 to 2, n-1, d 1 to 10. Why are we not writing ns to n-1, d 1 to 10? Because n-1 d is filled only after ns is filled. We have to include chromium and copper, and also elements which occur below this in the periodic table. You know, for chromium we write 4s1 3d 5, and for copper we write the electronic configuration as 4s1 3d 10. Remember that. So to include these elements also, we write the general electronic configuration as ns1 to 2, n-1 d 1 to 10. Now we define a transition element as one which has an incompletely filled d orbital, either in its elemental state or any one of its oxidation states. To make it clear to you, I will give some examples. Take scandium for example, which has 21 electrons. Its outermost configuration is 4s2 3d1. It has a partially filled d orbital. Take copper. When you take copper configuration with 29 electrons, we write it as 4s1 3d10, isn't it? Though it is 3d10 here, in Cu2 plus, what is the configuration? Cu2 plus, that 4s electron is gone and one more electron from the 3d10. So it has 3d9 and incompletely filled d orbital. So that is the definition. Transition metal has an incompletely filled d orbital in its elemental state or any one of its oxidation states. You can show it taking any of these examples. But zinc, cadmium and mercury have the configuration ns2, n-1, d10. So in the elemental state, these three elements in group 12 do not have partially filled d orbital. Also, in the common oxidation state, which is mostly only +2 state, you do not have an incompletely filled d orbital. So it is not quite correct to consider zinc, cadmium and mercury as transition metals. This is one of the very important reasoning questions. You can be asked, why can't we call zinc, cadmium and mercury not as transition elements? No, I'm sorry, we can't call them as transition elements. Now, if you take the S block elements or the P block elements, you find a vertical similarity. The vertical similarity is due to similar electronic configuration, we know. The vertical similarity is such that the first group elements we call them as alkali metal family, second group as alkaline earth metals, and group 17 we call it halogen family, group 18 as noble gases, and group 16 as oxygen family. They are almost studied as a family of elements. Such vertical similarities you don't come across among these transition elements. The horizontal similarity is of greater importance here, more noteworthy here among these transition elements. Though vertical similarities do occur among these, they are of not much relevance. For example, you can take nickel, palladium, platinum. Do you remember where these elements are put to use? Nickel, palladium, platinum, isn't it? Where do we come across these elements? In organic reduction reactions. Catalytic reduction to add hydrogen to organic compounds, or to reduce with hydrogen in the presence of a catalyst, we can use nickel or palladium or platinum, any one of these. So that is the similarity here you notice. And also copper, silver, gold are called coinage metals. These have similar properties, not only that they occur together. Now, most of the properties of transition metals can be explained using the concept that they have incompletely filled d orbitals. That means the partially filled d orbitals only give rise to some very important properties of transition metals. Before taking it up for discussion, we will discuss some general properties of transition metals. The first one is metallic nature. So, we will first take up metallic nature. We will call them general characteristics. They are all very strongly metallic with typical properties of metals like malleability, ductility, thermal and electrical conductivity, and high melting points. You know that the high melting points of metals are due to the strong interatomic attraction. For this we will recall the earlier concept of metallic bond, where metals are considered to be having the metal ions embedded in a pool of electrons. Now in transition metals, you have a large number of valence electrons. Not only the ns electrons, we also have n-1 d electrons as valence electrons. When all these electrons are forming the electron sea or electron cloud with the metallic ions embedded in them, it gives rise to very strong interatomic bond. So transition metals have very high melting and boiling points. So they are typically metallic. Secondly, decrease in atomic ionic radii. You find a gradual decrease in atomic and ionic radii as you go from left to right along a row of transition metals. The reason is the same as you give for decrease in atomic radii as you move from left to right, even in periods 2 and 3. The nuclear charge increases and the incoming electron enters the d level, where the screening of one d electron by the other is much less compared to the s and p electrons. So there is greater effective nuclear charge and greater pull on the outermost electrons. Hence, we can explain a decrease in the atomic and ionic radii as we move from left to right. The decrease in the atomic and ionic radii of the 3 rows of transition elements are shown in this figure. As you move from group 3 to 12 along the x-axis, you see the atomic radius decreases. This same is the case with the other 2 rows also. But there is one thing that you observe here, that the line showing the atomic radii of 4d elements and that showing the atomic radii of 5d elements lie very close. How do we explain this? For this, we have to again have a look at the periodic table. We saw in the figure that the 4d elements and 5d elements have very close values for their atomic radii. The curves lie very close by. See, the first element of the 5d series is lanthanum, having an atomic number 57. Next element shown here, hafnium, has an atomic number of 72. That is because 14 lanthanoid elements which lie behind lanthanum are put in this one space there and shown separately below because of their very similar chemical properties. Now, you find a gradual decrease in the atomic radii of these lanthanoid elements also. It is actually to a greater extent than what you notice in the d block elements. That is due to poorer shielding effect of f electron compared to the d electron. So, you find a very noticeable decrease in the atomic radii of these 14 elements. Now, if you take the 4d and 5d elements, 5d elements are one shell above. They are in the 6th shell. The 4d elements are in the 5th shell. But still, the increase that you expect in their atomic radius due to the addition of an extra shell is compensated by the decrease in the atomic radii in the preceding 14 elements. Hence, the 5d elements have very close values for the atomic radii with their counterparts in the 4d series. I suppose it is clear to you. So, the question can be asked in two ways. The 4d elements and 5d elements have very similar values for their atomic radii. Why? Or typically, specifically taking zirconium and hafnium. Actually, zirconium has an atomic radius of 160 picometer and hafnium has 159 picometer. Zirconium and hafnium, though having a large difference in their atomic number, have very similar atomic radii. Why? The answer is simply due to lanthanoid contraction. This decrease in the radii of the lanthanoid elements is given the name lanthanoid contraction. So, the reason is simply due to lanthanoid contraction. Or in other words, if you are asked what is the effect of lanthanoid contraction, you have to say the elements of 4d series and 5d series of transition elements have very similar values for the atomic radius. I suppose it is clear to you. Now, the third property that we have to consider is ionization enthalpy. Now, when you say that there is a gradual decrease in the atomic radius of the transition elements as you move from left to right, you expect the ionization enthalpy to increase, isn't it? As the size becomes smaller, the energy to remove the outermost electron should become higher. Ionization enthalpy should increase. Yes, it does increase, but it is not very regular. You don't find a regular pattern in the values of the ionization enthalpies of the 3D series. It is because the energies of the 4s orbital and 3d orbital they lie very close to each other. So, when you remove the outermost electron, there is electron movement between the two orbitals, two levels, and hence it gives rise to some irregularities in their ionization enthalpy values. But the common oxidation state for the transition elements is +2. So, for oxidate to realize the oxidation state of +2, we have to take into account the sum of the first and second ionization enthalpies. When you think of chromium and copper, see, for chromium, you know, it has a configuration of 4s1, 3d, 5, and for copper, you have 4s1, 3d, 10. Can you comment about the second ionization enthalpy values for chromium and copper? Would it be high or not so high? Can you give reason for whatever you say? See, when you remove the first electron, giving the first ionization enthalpy that is needed, it will be left with a stable half filled and completely filled 3D level. Hence, to remove the second electron, the energy required will be much higher, isn't it? So the second ionization enthalpy of these two elements will be much higher. You have to understand that. In the case of zinc, it has 4s2 3d10. So the two electrons are to be removed only from the outermost s level, which should be low. So for zinc, cadmium and mercury, the ionization enthalpy values will not be very high, but the other elements, it should increase. So we have discussed three general properties of transition elements. That is, we have discussed generally about their metallic nature, and we have seen and also given reason for the decrease in the atomic and ionic radii of the transition elements, and the change in the ionization enthalpies of the transition elements as we move from left to right.